Welcome to Agentic Era, where we explore the most disruptive breakthroughs in machine intelligence. Research from Princeton University and the Princeton Plasma Physics Laboratory introduces beacons, a framework for bounded error algebraically composable neural solvers. These solvers address the fundamental limitations of partial differential equation modeling by ensuring formal verification and zero extrapolation collapse. Unlike traditional models, beacons maintain structural integrity through complex algebraic compositions. The framework provides a mathematically rigorous foundation for simulating physical systems where errors were previously unconstrained. This represents a paradigm shift toward reliable, machine-checkable neural computation in high-stakes scientific domains. Scientists can now deploy neural solvers with mathematical certainty across diverse regimes. These architectures offer a path towards solving the most complex challenges in computational physics. Traditional neural architectures frequently fall into the interpolation trap when applied to computational physics. These systems demonstrate near-perfect performance strictly within the convex hull of their training data. However, they suffer from catastrophic structural divergence in out-of-distribution OOD regimes. A visualization of 2D data shows a cyan path of interpolation within the hull. Outside these boundaries, the standard neural network experiences total extrapolation failure. The true physical path continues smoothly while the model prediction jaggedly deviates. This failure mode is critical because physical simulations must often explore regimes beyond existing experimental validation. Relying on mere interpolation is insufficient for high-fidelity scientific discovery. The boundary of the convex hull acts as a hard limit for unverified architectures. Breaking this limitation requires a fundamental rethink of how networks represent physical laws. Constrained latent spaces in standard neural networks often inhibit convergence for complex partial differential equations. These architectures heavily penalize states that appear to violate physics during the training process. For highly nonlinear, coupled equations, the shortest path between valid solutions is often difficult to find. This path frequently traverses a ravine of entropy-violating states that the model cannot navigate. A 3D surface plot depicts valid peaks separated by a deep, dark red canyon. Standard models attempting to cross this ravine encounter breaks and failures in training. This dilemma forces a choice between physical validity and the ability to reach a solution. When constraints are too rigid, the network fails to find the global optimum. A fundamentally different approach is needed to allow traversal through these invalid intermediate states. This flexibility is essential for the convergence of complex fluid and plasma simulations. Beacons is a fundamentally unconstrained and formally verified framework for scientific machine learning. The system is built around several core modules, including a core kernel, verifier, and bounds estimator. It is designed to be algebraically composable, allowing deep expressiveness to emerge from shallow networks. Rigorous mathematically verifiable L-infinity limits ensure the model remains within worst-case error bounds. This move toward neural solvers specifically for partial differential equations marks a significant technical advancement. A central hexagonal architecture connects various peripheral modules through a specialized circuit-like logic. By decoupling the solver from rigid constraints, Beacons achieves higher stability than previous methods. The framework allows for the assembly of complex solvers from tractable, well-understood components. This modularity ensures that each part of the system can be independently verified. The resulting architecture is both flexible enough for training and rigid enough for formal proofs.
The first core technology involves a priori error bounds to ensure stability. This method predicts stability before the first training step ever occurs. By utilizing the method of characteristics, the system predicts continuous derivatives far from training data. It shifts the paradigm from interpolatory guessing to rigorous extrapolatory bounds. These bounds are derived from classical Muscar and Pincus theorems for function approximation. A line graph shows a cyan curve fluctuating safely within pink dashed lines. These lines represent the L-infinity error bound limit that the model cannot cross. Unlike standard networks, gradient descent can traverse physically invalid regions freely in this framework. The system is guaranteed to converge near a valid region in the mathematical limit. This provides a safety net for neural networks operating in unknown physical regimes. Predictable bounds are the cornerstone of reliable scientific machine learning.
Algebraic composability serves as the second core technology within the beacons framework. This approach generalizes the concept of flux limiters for the modern neural network era. Deep architectures are assembled by composing multiple shallower and highly tractable networks. Massive L-infinity errors from discontinuous shocks are mathematically suppressed by this composition method. The system decomposes a shock into a smooth Lipschitz continuous function and a discrete step function. These components pass through a recombination unit to maintain tight error bounds. Even in infinite-dimensional function spaces, the model preserves its mathematical integrity. A flowchart shows the transformation from a jagged shock into a smooth, bounded wave. This mechanism prevents the numerical instabilities typically associated with high-gradient regions in fluid flow. By managing discontinuities algebraically, the network avoids the common pitfalls of standard deep learning. It allows for the representation of complex physics without the risk of uncontrolled error growth. The verification stack moves the system from symbolic logic to optimized C code. It begins with a domain-specific language based on Racket for hyperparameter and equation specification. Users define systems like the Euler equations through high-level symbolic logic. An automatic code generator then synthesizes optimized C code for standalone execution. This code can be integrated directly with multiphysics frameworks such as GKEL. Finally, an automated theorem prover generates machine-checkable certificates of correctness. These certificates fully respect IEEE 754 floating-point standards for numerical accuracy. The stack ensures that every step from theory to hardware execution is formally verified. This eliminates the black box nature of traditional neural network deployments in science. Providing formal proof of correctness is essential for mission-critical engineering applications. The resulting code is both high-performance and mathematically sound across all platforms. A series of benchmark tests evaluate beacons against standard neural network architectures. These tests are designed to push standard models to their breaking points using linear and nonlinear equations. The benchmarks include linear advection, the Invisib-Burgers equation, and the compressible Euler equations. Each test is conducted in both one-dimensional and two-dimensional settings. Researchers compared standard 6- and 8-layer networks against beacons' counterparts with identical parameter counts. This ensures that any performance gains are due to the architecture rather than model size. The visual graphics show a simple wave entering a complex grid to become a fluid vortex. These tests evaluate how well the networks can handle wave propagation and shock formation. Success in these benchmarks demonstrates the robustness of the bounded error approach. The goal is to identify exactly where standard architectures fail and how beacons succeeds. This comparative analysis provides a clear metric for the framework's superiority. Test 01 focuses on 1D linear advection to determine if the models can track wave speeds. Standard 6-layer neural networks consistently overestimate the advection speed during the simulation. These models also exhibit massive overshoots and undershoots that violate the physical profile. Meanwhile, standard 8-layer networks significantly underestimate the speed of the moving wave. Line graphs show these standard models shifting significantly away from the numerical target over time. In contrast, the beacon solutions perfectly track the formally verified numerical solution. There is zero phase lag observed in the beacon's output throughout the entire test. The model remains aligned with the ground truth even at late time steps. This result proves that beacons eliminates the wave speed misprediction common in deep learning. Accurate velocity tracking is a fundamental requirement for any reliable fluid solver. Without it, the simulated physics quickly becomes decoupled from reality.
Conservation metrics for the 1D linear advection test highlight the stability of the framework. The goal is to stop the mass loss cascade that typically plagues neural solvers. An 8-layer standard neural network shows a total conservation error of negative 4,391.64. In comparison, the 8-layer beacons model achieves an error of only positive 49.57. This represents a massive 88x reduction in conservation error compared to the baseline. The L-infinity final frame error also drops from 0.97 in the standard model to 0.60. Beacons remains comfortably below its mathematical worst-case bound of 0.70. This radical stabilization of conservation over time is a key breakthrough for the framework. It demonstrates that the theoretical bounds successfully constrain the behavior of the network. Standard architectures cannot provide these same guarantees for mass and energy conservation. This evidence supports the use of beacons for long-term physical simulations. The 2D linear advection disk test evaluates the preservation of multi-dimensional geometry. A standard 8-layer architecture fails to preserve the circular shape of the disk as it moves. Instead, the disk progressively distorts into an egg-like geometry while lagging in speed. Heat maps show this structural collapse as the shape becomes a diagonal oval over time. The beacons architecture preserves the disk perfectly with no observable distortion. It tracks both the geometry and the velocity of the disk flawlessly across the domain. The L2 error across all frames drops from 22.77 for the standard model to 6.74 for beacons. This quantitative improvement confirms the visual evidence of shape preservation. Maintaining geometric integrity is vital for simulations involving complex moving boundaries. Beacons ensures that the qualitative features of the data are not lost during propagation. This success in 2D extends the framework's utility to more realistic physical problems. Test 02 addresses the nonlinear shocks of the 1D inviscid Burger's equation. Standard architectures completely mispredict both the right-moving shock speed and the left-moving rarefaction speed. These models also tend to diffuse the qualitative structure of the shock front over time. Line graphs at multiple time steps show the standard models deviating from the numerical solution. Beacons perfectly captures the top hat initial value problem without diffusing the structure. The beacons lines overlap almost perfectly with the numerical ground truth in all frames. It accurately captures the steep gradients associated with nonlinear shock waves. This ability to master shocks is essential for modeling high-speed fluid dynamics and plasma physics. By halting the diffusion of the wave profile, beacons maintains high-fidelity results. The framework demonstrates its capability to handle the most challenging nonlinear phenomena. It succeeds where standard deep learning models traditionally fail due to excessive smoothing. A phenomenon known as the depth paradox appears during the analysis of the Burger's equation results. In standard neural networks, adding more layers typically leads to a slight reduction in error. However, the 6-layer beacons architecture represents the optimal mathematical fit for this specific nonlinear class. This shallower model actually outperforms the deeper 8-layer beacons version in conservation metrics. The 8-layer standard network has a conservation error of 1442.49, which is quite high. The 8-layer beacons model reduces this significantly to negative 35.54. Remarkably, the 6-layer beacons model achieves near-perfect conservation with an error of only negative 0.56. This insight suggests that architectural design is more important than raw depth. Choosing the right mathematical structure allows for superior performance with fewer parameters. The depth paradox proves that beacons can be more efficient than standard deep learning. It highlights the value of using a priori knowledge to guide model selection. The 2D inviscid Burger's disk test further demonstrates the halting of geometric diffusion. Standard architectures overestimate the propagation speed so drastically that the shape crashes into the boundary. The disk distorts into a sharp, pointed cone rather than maintaining its physical profile. Heat maps show a clear failure to capture the correct velocity and geometry of the wave.
Beacons matches the numerical ground truth almost identically in both shape and velocity. It preserves the elliptical shape with a rounded end as expected from the underlying physics. The final frame L2 error plummets from 37.41 in the standard model to 2.68 in Beacons. This massive improvement reflects the framework's ability to handle multidimensional nonlinearities. By preventing the premature boundary collision, Beacons proves its reliability for complex dynamics. The results confirm that bounded error solvers are necessary for stable long-term predictions. This benchmark reinforces the framework's superiority in high-dimensional shock problems.
Test 03 involves the compressible Euler equations, representing a significant multi-physics stress test. This challenge requires solving coupled conservation laws for mass, momentum, and total energy simultaneously. The state vector includes density, momentum density, and total energy density components. Training data for this test was generated using unverified high-resolution numerical solvers. Consequently, the Beacons bounds are proved conditionally based on the accuracy of the underlying solver. This setup tests the model's ability to handle interacting physical fields in a complex environment. Solving these equations is critical for aerodynamics, astrophysics, and fusion research. The complexity of the coupled variables makes this a difficult target for any neural network. Beacons must maintain stability across all three conserved quantities throughout the simulation. This test serves as a rigorous evaluation of the framework's real-world applicability. Success here indicates that the model can handle integrated physical systems.
The 1D SOD shock tube simulation specifically tests the capture of contact discontinuities. Standard architectures completely diffuse the qualitative structure of the density profile. They fail to represent the sharp stair-step features of the contact discontinuity and the shock front. Instead, the standard models produce smooth, gradual slopes that do not reflect the physics. The 8-layer Beacons version tracks the high-resolution numerical solution with high precision. It captures all three wave speeds correctly and maintains the sharp profiles of the discontinuities. Graphs of density versus position show Beacons following the stair-step profile almost perfectly. This precision is vital for capturing the fine details of fluid interactions and shock waves. Standard networks often require massive amounts of data to achieve even a fraction of this accuracy. Beacons achieves it through its inherent architectural constraints and formal verification. This result demonstrates the framework's power in handling the most difficult 1D fluid phenomena.
The 2D Euler quadrants problem provides a highly complex ground truth target for the framework. This simulation features multiple intersecting shockwave fronts and intricate fluid structures. A mushroom-like central cloud forms as the waves interact within the four quadrants. There is also a distinct bright spike, often called a ray, in the top right quadrant of the domain. The problem involves both concave and convex propagating wavefronts that must be correctly modeled. This benchmark is a standard test for high-performance fluid dynamics solvers because of its complexity. Any failure in capturing these features indicates a fundamental weakness in the numerical method. The detailed heat map shows a rich tapestry of yellow and purple shock interactions. Modeling this correctly requires the network to understand the nonlinear coupling of the Euler equations. It is the ultimate test for the Beacons framework in 2 dimensions. Success here proves the model can handle extreme structural complexity.
Structural architectures experience structural collapse when faced with the extreme complexity of the 2D Euler problem. These models exhibit complete diffusion of the critical qualitative structures seen in the ground truth. Analysis shows that the protruding ray structure in the top right quadrant is entirely missing from the prediction. Furthermore, the bottom left wavefront is incorrectly predicted as concave instead of convex. The resulting heat map is a blurry version of the target where sharp features have been smoothed out. This loss of detail makes the model unsuitable for actual scientific or engineering work. Structural collapse occurs because the standard network cannot resolve the high-frequency components of the shocks. It tends toward the simplest average solution rather than the physically correct one. This failure highlights the dangers of using unverified neural networks for multiphysics problems. Without rigorous bounds, the model cannot maintain the integrity of complex fluid interactions. The lack of structural fidelity leads to incorrect physical conclusions. The beacon's architecture achieves verified precision on the 2D Euler problem, preserving extreme complexity. It successfully predicts the overall shape and propagation speeds of all constituent waves in the simulation. Unlike the standard models, Beacons captures the intricate protruding ray structure with high clarity. It also maintains the correct convexity of the bottom left wavefronts throughout the process. The resulting heat map closely matches the high-resolution ground truth, including the central mushroom shape. This level of detail is a direct result of the framework's bounded error and composable design. By accurately modeling these features, Beacons proves it can handle real-world fluid dynamics challenges. The framework provides a level of structural fidelity that was previously unattainable for neural solvers. This precision is verified through machine-checkable proofs that ensure numerical reliability. Researchers can trust these results for complex multiphysics analysis. It marks a turning point for neural network applications in scientific computing. Metrics for the Euler equations show exponential reductions in conservation drift when using the new framework. In the 1D test, the total conservation error for the 8-layer standard model is over 5,000 units. The 8-layer Beacons model reduces this error to negative 211.28, showing massive stabilization of mass loss. Similar improvements are seen in the 2D test, where the L2 final error is analyzed. The standard architecture has an error of 25.84, while Beacons achieves a much lower error of 2.95. These numbers confirm that the framework transforms neural networks into rigorous simulation engines. No longer are these models just lossy heuristics that approximate physics. They are now mathematically sound tools capable of high-precision work. The massive reduction in conservation drift is particularly important for long-duration simulations. It ensures that the total mass, momentum, and energy are preserved as required by law. These metrics provide the empirical proof needed to validate the Beacons approach. The framework consistently outperforms standard models across all measured dimensions. The vision for the future involves a neural-symbolic approach to computational physics. Neural networks are viewed as arbitrarily efficient compressors of algorithmic information. The Beacons framework acts as a lossless compiler that converts physics equations into verified neural blocks. A flowchart shows a partial differential equation being discretized and solved by this compiler. The result is a 3D formally verified neural network block that can be deployed anywhere. This shifts the role of the neural network from a lossy heuristic to a predictable engine. We are moving away from unprincipled training toward a more structured and verified paradigm. This compiler approach allows for the rapid generation of efficient solvers for new physical laws. It bridges the gap between traditional numerical methods and modern machine learning. By ensuring that the compression is lossless, the system preserves all physical information. This neural-symbolic future promises to revolutionize how we approach scientific computation. This roadmap leads to a foundation model vision for physics based on a mixture of experts' MOE architecture. Specialized Beacons modules will be pre-trained for distinct laws of physics, like fluid dynamics, thermodynamics, and electromagnetism. These experts can then be coupled into a single multi-physics supernetwork for complex simulations. The diagram shows multiple specialized modules feeding into a central glowing structure. This supernetwork learns to seamlessly combine solutions for domains where different physical laws interact. Every component within the system remains fully formally verified through the Beacon stack. This goal represents the next generation of scientific modeling tools. Coupling these experts allows for the simulation of entire physical systems, from fusion reactors to weather patterns. The modularity of the design ensures that each expert remains accurate within its domain. This foundation model approach provides a scalable and reliable way to tackle multiphysics challenges. Beacons redefines the boundaries of neural solvers through machine-checkable correctness. The framework provides fully executable proofs that comply with strict IEEE 754 standards. By utilizing the method of characteristics, it prevents extrapolation collapse. This ensures rigorous worst-case L-infinity error bounds for every simulation. Algebraic composability allows the system to tame complex discontinuities. This generalizes traditional flux limiters for use within deep neural networks. The resulting framework offers infinite expressiveness without sacrificing mathematical reliability. Researchers at Princeton and the Princeton Plasma Physics Laboratory have moved beyond simple interpolation. This architectural shift creates a foundation for verified large-scale scientific modeling. Neural networks can now function as entirely predictable engines for complex physics.